Hi, I'm Iona. I'm an application scientist at Edinburgh Instruments, and welcome to this photoluminescence quantum yield tutorial. In this tutorial, I'll be showing you how to perform quantum yield measurements of solutions using the SC-30 in the FS5. If you've not done so already, make sure the SC-30 is inserted into the FS5. Fluorical software will automatically recognize this sample module being inserted. Before we perform quantum yield measurements, we must know the absorption and emission properties of our samples. This is so we can select the correct excitation wavelength. For this demo, the sample I'm using is rhodamine 6G in ethanol. That means that the blank is also ethanol. To select an appropriate excitation wavelength, we must ensure there is no overlap of our excitation and emission peak areas. This is so that we can accurately count the number of photons within each. For this sample, the emission starts at around 500 nanometers, so we recommend selecting an excitation wavelength at least 20 nanometers before this onset. That means for this sample we will use an excitation wavelength of 480 nanometers. To determine the measurement parameters, first we put the blank into the SC-30. For quantum yield measurements, we measure the scattered excitation photons. Since the blank doesn't absorb the excitation light, the scatter peak will have a higher intensity compared to the sample. So we use the blank to set our measurement parameters. To set our measurement parameters, we must open the signal rate window. First, we'll ensure that the correct light paths are selected. This will be the xenon lamp for the source light path, and for our detector, it will be the visible PMT with integrating sphere. Selecting the correct detector light path ensures that the right correction files will be applied to our data. Next, we set the excitation wavelength to 480 nanometers. We set the bandwidth to around 3 to 5 nanometers, but we must make sure our reference detector is not saturated. We then must set our emission bandwidth narrow, for example 0.1 nanometers. This prevents our emission detector from saturating, as we also set the emission wavelength to 480 nanometers. We then gradually increase the emission bandwidth until we reach about 1 million counts per second for the emission detector. To collect our measurement, we go to Spectral, then Emission Scan. For the correction options, all should be enabled, including subtract background, excitation correction, and emission correction file. We then set the scan range. We recommend you go from 20 nanometers before the excitation wavelength to 20 nanometers past the end of the sample emission. Next, for the step size, we recommend this to be 10% of the widest bandwidth. In this case, the bandwidth was 3.5 nanometers, so the step size will be 0.35 nanometers. This is so that there is enough data points to accurately integrate the peak area of our excitation peak. Finally, I will select a dwell time of 0.2 seconds, which is our recommended minimum for quantum yield measurements. We can now start the measurement. Now that the measurement has finished running, we can go to Properties and rename this blank. Now we swap our blank for our sample. This must be the same volume in an identical quartz cuvette. We now run the measurement for the sample. We must make sure the parameters are exactly the same. We can do this by using the Rerun button on the toolbar. Start the measurement keeping all settings the same. Once the measurement is run, we go to Properties and rename this scan Sample. To calculate the quantum yield, first we join the two scans together into one window. Then we launch the quantum yield wizard from the toolbar. In the general settings, we select our sample type and measurement type. For this measurement, we measured the scatter and emission peaks in the same spectrum, so we leave the measurement procedure option unselected. Then click OK. Check that the Quantum Yield Wizard has correctly assigned the spectra to blank and sample before clicking Validate. The software will estimate the scatter range, which can be adjusted if needed. Then we will assign the emission range on the plot. This can also be defined by typing upper and lower limits. We then click Calculate to get our quantum yield. In this case, for our sample of rhodamine 6G, the quantum yield is around 96%. So that's how you measure the quantum yield of solutions using the SC-30 in the FS5. I hope you found this tutorial useful. Like and subscribe for more content. Thank you for watching.